Hey guys. Today I'd like to cover an example of ordinary least squares called the simple linear regression model. Now, what is ordinary least squares? Well, from Wikipedia, it chooses the parameters of a linear function of a set of explanatory variables by the principle of least squares. So let's look at the components of this definition. So what we're doing today is we're choosing the parameters, or solving for the parameters, of a linear function using one explanatory variable, x. And here's the data. And so we have x and y, and we have 5 observations for x and y here. So 5 observations total. X increases in the observation count from 20, 30, 60, 90, and 100. And then y also increases 10, 20, 30, 40, and 50. And here's our simple linear regression equation. And so the parameters of the linear regression equation that we're solving for are a and b. So we're solving for a and b in this linear function. And so if we go back to the definition, these are the parameters that we're choosing or solving for, and our linear function. This is our linear function, and the explanatory variable is this x variable here. Now, what's the principle of least squares, this process? Well, the principle of least squares minimizes the sum of the squares of the differences between the observed dependent variable in the given data set and those predicted by the linear function. So we're minimizing the sum of the squares of the differences between this y and our prediction of y. And so we're going to be predicting y with our simple linear regression equation, but our prediction won't be perfect. But we're going to choose this prediction of y such that the difference between our observations of y and our predictions are as small as possible, as close to 0 as possible. So let's actually do it. We'll solve for a and b. We'll create our simple linear regression equation, our linear function, and then we'll input some values of x and estimate y. First, let's create a scatter plot of x and y. And I'll put this over here. So we can see we have a scatter plot of x and y. This is our x-axis here, and this is our y-axis. And so for each observation of x and y, we have a data point in the scatter plot. Our first data point is 20 and 10. Our second data point is 30 and 20. And our third data point, 60 and 30, and so on. And so from this scatter plot, if we were to draw a line that represents the relationship between x and y, we would draw it right through this data, and that line would have a positive slope, and it looks like it would have a positive y-intercept too. And so that's actually what we're doing. We're creating that line, the simple linear regression line. And that line we're going to create, again, such that the difference between these observed values of y and our predictions are as small as possible. Okay. So OLS, it uses averages. Now, other forms of regression may use medians or other quantiles in quantile regression, but here we're using averages. So I'm going to find the average of x and the average of y. And this is a open source version of Microsoft Excel. And I'm putting in some anchors because I'm copying this down and I don't want my row number to change. I am okay with changing the column when I copy that over. And here we have averages of X and Y. Okay, so X's average is 60, Y's average is 30. That makes sense. Our averages, our values here in the middle for X and Y are 60 and 30. And now we want to find the difference between X and its average and Y and its average. And so as we go through here, you can kind of see the formations and of the linear regression equation, how we create that line such that it's the best fit line for the data that represents the data. And we have some negative values here, right? When X is less than the X average, we have the differences that is negative. And then we have positive values here too. Now, the first component, the first parameter we're solving for is B. And then once we find B, we can solve for A. And so this part B here is first. And to find that, we need to calculate the covariance and the variance of X. So the covariance of X and Y is the sum of the products of these differences divided by the degrees of freedom. And so let me put that in here. And we're going to find the product. And then the sum of the products. And our degrees of freedom, n-1. I'll use the count function here. You don't have to use the count function, but if you'd like to delete some values of X, then you could do that and see how the regression equation changes, and, or delete values of X and Y and so on. But the covariance. So our covariance of X and Y. We're going to take the sum and divide by our degrees of freedom. And so our covariance is 550. Now the covariance of X and Y is a measure of the, it's kind of the relationship between X and Y, but it's how X and Y fluctuate and vary together. Now here we see the covariance is positive, but we can't really say too much else besides that, because there's a certain scale to X and Y, and so covariance is related to correlation, but we don't really know how strongly X and Y are related to each other. But that's okay for our purposes. We're solving for a parameter, so okay. And we want to use the function for a sample variance when we're calculating the variance of X. So again, sample variance of X, we have a sample here. This is our sample data, and we don't know, we don't have population data, entire data set for the population. That may be massive in nature. We only have a sample. And so that's what we have to use to infer things about the population. And so the B and A here, parameters, are actually estimates of the population parameters, beta and alpha. So in this simple case, you don't need to know all of that. But let's continue on here. So b is equal to the covariance of x and y over the variance of x. Okay, so our b is 0.44, and that's the slope of our regression line. If we were to draw a line here that would best fit the data, well, that line would have a slope of 0.44. And if x was equal to 0, then we would have a y-intercept equal to 3.6. 3.6. So if you can imagine on the y-axis, sort of where our regression line begins maybe, but we may have some negative values of x and maybe even y2. So, but the y-intercept, where the regression line intercepts the y-axis when x is equal to 0, that's 3.6. And here's our, that's it. Now, let's create our regression equation using parameters a and b, and let's estimate y using a value of x, and say x is equal to 25. What would be a good estimate of y given x of 25? I'll put the y here, and let's actually put these parameters in here. So we have 3.6 plus b, our slope, times x. Okay, 14.6. So when x is 25, our sample, when x is 25, our estimation of y is 14.6. Now if we look at the sample data, we look at x here and how it changes in the observation count here as we're increasing. Between 20 and 30 is 25, and maybe we could estimate that y would be close to 15, and sure enough, that seems to be the case. 14.6, we're pretty close to our estimate. So again, we've just solved for the simple linear regression equation. A, our first parameter here, the y-intercept is 3.6. B is our slope, that's 0.44. And when you have these, when you solve for these parameters, you can input values of x and estimate values of y. Now when x is 25, we estimated y to be 14.6. What about y when x is equal to 30? Now, we estimate y to be 16.8 when x is 30. But if we look at our sample data, when x is 30, y is actually 20. So the observed value of y is different than our predicted value of y. And so that's called an error, or a residual, in the case of sample data and using our sample value, sample statistics here that we've calculated. So we've actually chosen we've chosen our parameters such that our estimation of y will be as close to y as possible, and so that the difference between y and our estimation is as close to 0 as possible, but it's not 0. So there is some error, and that's to be expected. You're going to have some error when you calculate, when you use ordinary least squares, but unless of course you're x and y are perfectly related to each other, in which case you can perfectly estimate y, but that's not often the case. So with this example, you can change values of x and y. For instance, I'll change this x, and as we change values of x, the parameters change. We now have a negative slope, and our y-intercept is relatively higher. And if we look at our scatter plot, that's also changed. It's also adjusted. And so again, our best fit line here will actually be negative, and we'll have a high y-intercept here. And but we can see what's actually happening in the ordinary least squares process as we change values of x and y. Now try this for yourself. Change values of x and y here. What happens to the parameters b and a when we change x to b so that it's maybe that all the x values are the same? I'll let you guys do that for yourselves. So I'll see you next time.